Okay, good morning. So, if you remember, we talked about the notion of metric. So last time we learned about that we have an Euclidean metric. So if we write it on the two dimensions, for example, so let us say that I have 2 points with coordinates x sub 1, y sub 1, and x sub 2, y sub 2 in the plane. And then this was the Euclidean metric that we have. So it is the second root of, let me write it in this way. Instead of writing the second root, so let me write it as x1 minus x2 to the power of 2, and then plus y1 minus y2 to the power of 2. And instead of writing it as square root, I can have it as 1/2. So that was the Euclidean metric. And then we also learned about another metric, which is taxicab metric. Okay, so if you don't mind, let me write E for Euclidean and T for taxicab metric. And then we had these two, yes? x2, y2 is equal to the absolute value of x1 minus x2 plus the absolute value of y1 minus y2. Yes? Okay, and then I asked the question, can you see these two different metrics? We learned about that they have different properties. So, I mean, intuitively, it was not that clear. If you know everything about this metric, it is not immediately evident how this metric will behave. But this was the similarity between them. But if you want to see the similarity between them, we learned that we can put them in one single formula. So we introduced this formula. So we said that, okay, we can define a metric d sub p so that x1, the distance between these 2 points, can be written in this form. Yes, I can write it as x1 minus x2 to the power of p plus y1 minus y2 to the power of p and then to the power of 1 over p. So I'm not claiming for the time being that this is a metric, but I'm claiming that these two are particular cases of this general formula. So if you choose p to be 1, then D1 is actually the taxicab metric. Yes, because if I replace P with 1 everywhere, this will reduce to this formula. And if I change P to 2, then this becomes exactly that one, because in that case, there is no difference between absolute value of x1 minus x2 to power 2, which is even, and this one. And this will reduce to this. Okay. And that's why I wanted to try to motivate how abstraction works. So this is the way that a mathematician might think. So he or she will have this natural tendency to generalize things. So we learn that, okay, if it works for 2, if it works for 1, let us see if it also works for p greater than 2, for example. And then, of course, we can generate a formula for this. To the power of 1 over 3. Of course, I am generating a formula and I call it D3, but there is no guarantee that this D sub 3, for example, is a metric. Of course, if it is going to be a metric, I have to check the properties of a metric. This is not that hard to see if this D3 is 0 if and only if these 2 points are equal. Why? Because if these points are equal, it means x1 and x2 are equal, y1 and y2 are equal, so this becomes 0. On the other hand, if someone tells me that the output of D sub 3 is 0, this means that this non-negative number and this non-negative number has to be individually 0. So this will tell me that x1 is x2, y1 is y2. So these points are the same. It is clear that this is not sensitive to interchanging the points, because if I change them because of that absolute value, nothing will happen. So D3 is also symmetric. But the main problem again is it following the triangle inequality or not? And if you remember the proof of even this very natural metric for us following the triangle inequality was a little bit complicated. Okay, so this is the way a mathematician thinks, and then they do not actually stop for 3. They say that, okay, what's the problem if I go to higher and higher? Okay, so they might think about this scenario, yes? So d sub p x1, y1, x2, y2, and then I can write it as x1 minus x2 to the power of p plus y1 minus y2 to the power of p to the power of 1 over p. And then p is a real number, yes, greater than or equal to 1. Okay, for the case of p equals to 1, we don't have anything to prove because that becomes the taxicab metric, and we already showed that this satisfies all properties. So we can safely, for the time being, assume that p is greater than 1. Okay, and then you know that this satisfies all the properties of a metric. The non-trivial one is the triangle inequality. Okay, so if we want to show that all of them are actually indeed metrics, we need to prove that they follow the triangle inequality. Okay, so let me clean this here and write what we want to show, okay? So that I can start proving them. So instead of x1, if you don't mind, it would be easier for us to use different symbols here. So my goal is to show that the distance between, so I want to show this. I want to show that dp of a1, b1, and a3, b3 is less than or equal to dp of a1, b1, and a2, b2, plus the distance between a2, b2, and a3, b3, yes? Yes, if this is my goal, I want to show this. So if I translate this into the language of my formula, this becomes the absolute value of a1 minus a3 to the power of p plus b1 minus b3 to the power of p to the power of 1 over p is less than or equal the absolute value of a1 minus a2 . Yes, so that is what I want to show. And I'm assuming that p is greater than 1. Okay, so the goal of this lesson is to show that sometimes, so what you have, you started with the notion of a distance, you abstract the idea of a distance, and then you defined what is a metric, and then motivated by the taxicab metric and the Euclidean metric, you were motivated to artifact a function, but then you say that, okay, is this function a metric or not? You realize that this question is reduced to answering if this inequality holds or not. So it means that you are making a research problem within mathematics itself about proving something. So you construct your own problem and try to solve that problem yourself. But this turns out to be actually hard, and that is the goal of this session. I want to show you that this type of mathematics is also needed if you want to be good in mathematics. So you have to be creative, and some problems are really technical. They're not always conceptual. Okay, and then I present it hopefully in a polished way for you. So there are many scratch papers have been thrown into the wastebasket to be able to people to realize how to prove this inequality. But I want to present it in its final form in polished way, okay? So this is why we start with an inequality, which is also famous and carries the name of a mathematician, and that is called Young's inequality, yes? Okay. So what is Young's inequality? Young's inequality tells you that if x is a non-negative real number, y is a non-negative real number, and if p is greater than 1 and q is greater than 1 and 1 over p plus 1 over q is equal to 1, then from all of them, I can conclude that x times y is less than or equal to x to power p over p plus y to power q over q. Yes? So it's a very nice inequality, and the reason that I want to go through it is because even though this is really technical to prove, but fortunately everything is at the right level for a high school student to understand. Yeah, so that is a good thing to understand, that even so you know, so it shows that you really know a lot mathematics if you want to be creative and solve hard problems. Okay, first of all, let me see if it works. So are these conditions consistent? I would say yes. Why? Because, for example, if p is greater than 1, 1 over p is less than 1. Yes? Okay? And then if I move it to the other side, it becomes positive. And positive and smaller than 1. So it means that q has to be greater than 1. So these conditions are really consistent with each other. There is no inconsistency going on. Yes? Okay, we want to prove this. So I told you that before, usually one strategy to prove inequalities is to simplify them in a recursive way so that we reach to some inequality which is somehow guaranteed for us to be true, and then we can say, but of course this will not work here. Okay, so the idea is more subtle, how to prove this inequality. So the way we do it is, first of all, I would say that if x is 0, then I am done. Yes? Because if x is 0, the left-hand side becomes 0. This becomes 0. This tells me that y to the power of q is greater than 0 by multiplying everything by q, which is guaranteed to be true because y is non-negative. And the same reason, if y is equal to 0, this inequality is guaranteed to be true. So if x is equal to 0 or y equals to 0, there is nothing for us left to prove. So the only thing that we can consider, so we say that let x be positive abstractly and y be positive. So we want to prove this inequality only when x is strictly positive and y is also strictly positive. So how we can do that? So I would say that let y be a fixed positive real number. So what I did, I just fixed one positive y. We define a function. We define the function f defined on, this is the notation I want to use, the interval from 0 to infinity. So then the interval 0 to infinity is defined to be the set of all real numbers. So the set consisting of all real numbers such that x is greater than 0. So that's a shorthand notation for this set. So defined on this by this formula. F of x is equal to x to the power of p over p plus y to the power of q over q minus y times x. So it's also a standard trick. So it's not that hard. So this is one experience for you. You need to learn this and then see how it works. So what we are doing, I am saying that y is a positive number. Pick any y that you want to. And I want to show that this is valid for all positive possible x's. Okay? Because you are free to choose whatever you want to for y, it means that I am able to prove, so this means that I have already proven that this is valid for all possible x positive, y positive. Yes, so is the logic clear? So what we do, we fix a positive real number, And then I show that for that particular fixed positive real number, I show that this inequality holds for all x positive. Okay, so that's the logic. But to do that, I define a function on this interval by this rule. And that is exactly motivated by the form of my inequality. I just move this to the other side. Yes?
When you say that the function is defined on that interval, do you mean that the output?
No, defined means the domain is this. Yes. Okay. So if I want to look at this function now, what is y to the power of q over q is just a constant number for me. That's important because I fixed my y and q was already fixed. So this part is just a fixed number. The function part is this part usually and that part, and this is a constant multiplied by my x. So that's a function of x, but y to the q over q is a constant, p is also a constant, so my variable is y. Okay, and this is an interesting problem actually in matrix C if you want to. We want to find the minimum of this function. Okay, so what we do, I want to find the minimum of my function on this interval. So what we do, the first thing we do, we have to differentiate the function. Yes, so we differentiate the function. Okay, so what happens? This p goes down, cancel that p, this becomes x to the power of p minus 1. But because I'm assuming that y is a fixed constant number, everything vanishes here. And this is a constant multiple of x, so its derivative becomes y. So that's the derivative. And I want to find the minimizer of my function. So according to what we have studied before, so I put it equal to 0 and try to find a possible minimizer for my function. So this gives me x to the power of p minus 1 is equal to y. And because p is assumed to be positive, greater than 1, this is positive. So here, what I say, x is y to the power of 1 over p minus 1. And because I am working in the domain of positive x's, I really don't need to be worried about if I need to put a plus or minus 1 in the case that is even or not. So this is the only candidate for the minimizer of my function. But of course, this will give me a local minimum or maximum, not guaranteed, it's not global. Okay, so but how should I find that? So if you remember this algorithm, if I want to find the minimum of my function on this interval, so what I need to consider is that point and also the endpoints here. Yes, so what we do, first of all, let me calculate f for that particular value. So y to the power of 1 over p minus 1. I want to see how much is this value. What is this value? So what I need to do, I need to replace every appearance of x in my function but that variable. So remember, this is just a fixed number. So what I do, I put it there. So this becomes y to the power 1 over p minus 1 to the power of p, and then divided by p. And then I have y to the power of q over q minus y times x, but x is this one again. And I have to simplify this as much as I can. This is just algebra, simple algebra. So this becomes y to the power of p over p minus 1 over p plus y to the power of q over q minus y. So here the exponent is 1. I have to add them. So it becomes 1 plus 1 over p minus 1. Of course, if I simplify that, this becomes p over p minus 1. So that's exactly what you see here. Yes? Okay. And then what? Something we need to check now here. So is this condition I haven't used so far. So let us see why this is good for. So here, if I go here when 1 over p plus 1 over q is given to be 1. So if I move this to the other side, so this becomes 1 over q is equal to 1 over 1 p minus 1. If I take the common denominator, so this becomes p minus 1 over p. Yes? And if I swap these two, so Q becomes P over P minus 1. So the combination that appears here is actually nothing except RQ. So what we do, I put Q there. So this, I come back here again in this line. So this becomes equal to y to the power of Q over P, yes, plus y to the power of Q over Q minus y to the power of Q. Yes, and it's a very, very nice combination because now I can factor a y to the power of Q out. Yes, so from here 1 over P is left. From here 1 over Q is left. And from here minus 1 is left. But 1 over P plus 1 over Q is equal to 1, so this becomes 0. Yes, so this becomes just 0. So I was able to calculate the value of my function at this point. So the value of my function at this is 0. Okay. Okay, but is it a minimizer or might be a maximizer? Yes, because we still don't know, is it a local minimum or a local maximum or a terrace point? So I think in this case, it is easier to use the second derivative test. So I take another derivative from my function. So the second derivative of my function is equal to P minus 1 goes down, x to the power of P minus 2. And of course, y is a constant, its derivative becomes 0. And then what I have to do, I have to put this here and see that how the second derivative looks like. Yes, y to the power of this one. And of course, you really don't need to calculate, I would say y, because this becomes P minus 1, and then I have y to the power of P minus 2 over P minus 1. Yes, but this is guaranteed to be positive because P is greater than 1. So this part is positive. It might happen that the exponent is negative, but doesn't matter because y is positive. Even if the exponent is negative, this combination is positive, that combination is positive because P is greater than 1. So this means that this is positive. So the first derivative is 0, and the second derivative is guaranteed to be positive. So this means that this number is a local minimizer, not a maximizer. But it's not guaranteed that this is the lowest possible value unless we also check that the value of the function at these two ends are higher. But this is very easy to see, yes, because if in principle, x is not 0 is excluded, but I can simply check the limits of my function when x goes to 0 from the right-hand side. Okay, then what happens for my function? This is my function. When I send x to 0, what do I get? This vanishes, so I get a positive value. Yes? And then what happens if I check the limits of my function when x goes to infinity? Okay, this part is just a constant, but because p, so I have a negative sign here, I agree. This one goes to infinity, this one also goes to infinity. So in technically speaking, this is infinity minus infinity, which is an indeterminate form again. But because p is greater than 1, this will dominate. Okay, so this means that this limit also becomes infinity. So what is my situation that I have? So at this particular number for x, the value of my function is 0. But when I approach to 0, it becomes a positive number, say like here. And when I go to infinity, it becomes infinity. I'm not sketching my graph. I'm not claiming that this is even close to what is real. But the features that I am interested in are captured here. So this means that this local minimizer is indeed the global minimizer. It's the absolute minimum. So what did I do? So I was able to show that the minimum of my function on the interval of interest is 0. Yes? And that's the global minimum. And then I am done. Because if the minimum is 0, it means that my function is always greater than or equal to 0. And that's exactly the inequality that I want to prove, yes? So this means that for all x positive, I was able to show that x to the power of p over p plus y to the power of q over q minus yx is greater than or equal to 0. Yes? But for any fixed positive y, so I can continue this argument for every choice of y. So you pick a y, I prove the same thing for every x. You pick another y, I follow the same strategy, and I will prove the inequality for that particular y again. So hopefully you agree with me that we were able finally to prove this inequality for all non-negative values for x and y. So we separated the problem for the cases 0 cases and non-zero cases. Okay, so that's you see that's exactly at the right level of the high school student mathematics. Okay, so, but now we want to go and prove another inequality, which is called Hölder inequality, yes? So it might be with a different pronunciation, Hölder. So what we are supposed to do now, this is the inequality. Let me use capital letters, you will understand why. So let us assume that x1 and x2, y1 and y2 are real numbers, any real number that you like. And again, p is greater than 1, q is greater than 1, and as before, 1 over p plus 1 over q is equal to actually 1. We want to prove this inequality. We want to prove that absolute value of x1 times absolute value of y1 plus absolute value of x2, absolute value of y2 is less than or equal to the absolute value of x1 to the power of p plus absolute value of x2 to the power of p to the power of 1 over p, and similarly something for y. So y1 to the power of q plus y2 to the power of q to the power of 1 over q. So this is the inequality that we want to prove, yes? So, this is a little bit more subtle. And I think the reason that I restricted myself to 2 variables for x, 2 variables for y, because I want to avoid complication coming from sigma notation and things like that. But you can immediately generalize this problem to any number of variables that you want to. Yes? Okay, so to prove this, I want to somehow use the Young's inequality in a wise way so that I can come up with this inequality. Okay, so what we define, I would say that first of all, if x1 is 0, what will happen? Yes? So if x1 and x2 are simultaneously 0, what will happen? I am done. Yes, because if x1 and x2 are simultaneously 0, the left-hand side vanishes, and the right-hand side, this vanishes, and this will be left for me, which claims this to be non-negative, which is true. Yes, because these are absolute values. And for the same reason, if y1 and y2 are simultaneously 0, again, I am done. So in my proof, I'm assuming that this is not the case that x1 and x2 are simultaneously 0, and this is not the case that y1 and y2 are simultaneously 0. So if I can prove this, then I am done. So this means that x1 and x2 are not simultaneously 0. What does it mean? It guarantees that this expression is non-zero. And I'm assuming that y1 and y2 are not simultaneously 0. It means that this is not 0. Okay, so this you remember. And now I introduce two variables. So I would say that let x1 be defined to be as absolute value of x1, capital X1, divided by a sub p. What do I mean by a sub p? Because I'm lazy to write over and over. So let us assume that this expression, I call it a sub p. And then I introduce another variable, so let me call it y1. I define it to be absolute value of y1 divided by b sub q. And what is b sub q? For simplicity of writing, I'm assuming that this is b sub q. Yes? Okay. Now let us see, can I use the Young's inequality for these variables? Let us check the conditions. Young's inequality works if the numbers involved x and y are non-negative. But I hope that you agree that this is possible. Why do you think it was important to assume that x1 and x2 are not simultaneously 0? Because I want to put this expression in the denominator of my variable, so it should be guaranteed that this is not 0, and the same thing here. So that was really crucial to start with this sentence that we separate the problem into two different parts. If they are simultaneously 0, it is guaranteed to be true, and if they are not simultaneously 0, this is the argument. Okay, so can I use the Young's inequality for x1 and x2, x1 and y1? The answer is yes, because x1 is non-negative by definition. It's the absolute value and is also positive. And then y1 is also positive. And p and q are guaranteed to be greater than 1. And 1 over p plus 1 over q is 1. So everything in Young's inequality is satisfied, so I can use the Young's inequality. Yes? So what does it mean? It means that I can conclude that x1, y1 is less than or equal to x1 to the power of p divided by p plus y1 to the power of q divided by q. Yes, this we have. But what is x1? x1 is by my definition this expression, so I replace it here. So this becomes capital X1 over AP multiplied by y1 is capital Y1 divided by BQ is less than or equal to x1 to power p. So if I raise it to power p, what will happen? This becomes the numerator to power p and the denominator to power p, but x1 to power p divided by a p. So if I divide this by an extra p, p goes here. Yes, so this is x sub 1 to power p divided by p. This becomes that expression. And then I will do the same thing here. Let me repeat this. y1 to power q, this to power q means this to power q, this to power q. But I also divide by an extra q, which will go to the denominator. So this becomes y1 to the power of q divided by bq to the power of q multiplied by aq. Yes? Okay, let's see what happens now. Can I simplify something here? So this becomes absolute value of x1, absolute value of y1 divided by AP times BQ, the left-hand side, is less than or equal to. So what happens here? So this one, okay, let me write it like this. So let me just write it like this. So this becomes x1 to power p divided by p AP to power p plus y1 to the power of q divided by q bq to power q. Okay, so I hope that you agree with me. I can repeat the same argument, but instead of starting with capital X1 and capital Y1, I can start with capital X2 and capital Y2. So I don't want to repeat this process, but I change my definitions. Instead of little x1, I define little x2. little y2, and then I repeat the same argument, so I will come up with this. So what happens, this becomes x2 y2 divided by AP BQ, and then less than or equal to x2 to the power of p divided by PA to power of P, AP to the power of p plus y2 to the power of q, and then I have q BQ to the power of q. Okay, and now more or less everything is done. So what do you think will be the next natural step? Look at what we want to prove. It motivates you. Of course, it is technical. So the person who actually used this in this wise way was smart. But I think next part will be, at least the next step is natural. What do you think I will do now? Look what we want to prove.
Maybe we can
Add them. Yes, it is more or less natural because I want to have this combination. And the good point is that the denominators are the same. So when I add them, actually these two will be added together is exactly what I want. So let us just add them. So this becomes x1, y1 plus x2, y2 divided by the same denominator. And then here, what do you think I will do? I want to avoid complications, and then the good point is that these two fractions have exactly the same denominator. So what I can do, I can add the numerators of them correspondingly. Yes, and then I put the same denominator there, and then plus, I will do the same thing here. This becomes y1 to the power of q plus y2 to the power of q, and then divided by q, b sub q to the power q. I think now everything is clear. Can you tell me what is this now? The definition of a sub p is on the board. So in your head, imagine that you raise it to power p. What will happen for this blue? What is inside this blue?
That's just one.
That's just one.
Yeah.
Yes? So that's just one. Because a sub p to power p, I will get rid of this when I raise it to power p. This is left, but that's exactly in the numerator. So this is exactly one. And then for the same reason, what is this one? This is also one. And then what is left for me? 1 over p plus 1 over q, yes? But what is 1 over p plus 1 over q is just 1. So you see that everything, when it works, suddenly everything fits together. So in mathematics, this isn't really happening. So if you have a correct idea, so you see that everything is fitting, exactly the combination that you need appears somehow. And then what happens, the last step is I have this less than or equal to 1. So this means the numerator is guaranteed to be less than or equal to the denominator. Or in other words, I can multiply both sides by that. So this implies that the absolute value of x1, absolute value of y1, plus absolute value of x2, absolute value of y2 is less than or equal to a sub p times a sub q. So now I realize that I totally messed up the formula. The formula is a product here. So yeah, that was my mistake, sorry. So this becomes AP times BQ. But AP times BQ is what? Is x1 to the power of p plus y1 to the power of, x2 to the power of p, and then to the power of 1 over p multiplied by y1 to the power of q plus y2 to the power of q to the power of 1 over q. Yes. So sorry for that. I don't know, I was using my memory, so this is it.
Just when we have an inequality and we're allowed to multiply by a positive number.
No, we are allowed. Yes, so these are non-negative numbers. I'm saying that this fraction is less than 1. It is guaranteed its numerator is less than its denominator. And I don't know why I messed up this sign. So that is a product there. Okay, so that might be a little bit disturbing. You couldn't see what's going on. Okay, anyway, but it works. So that's the Hölder's inequality. And I think you will see that there is no reason that I have to stop with two variables. If I increase this to more variables, I will have more variables involved. I will have only two expressions, but with more variables in each side of them. And the only reason that I avoided that, because then I had to use the sigma notation, and that might be a little bit confusing, but that is the essence of the problem. Yes?
With that, I mean that the process to the answer that you had, it's all in plus. Will all of those turn to multiplication?
Yes? No, so I didn't understand your question.
You know, the steps you did to the answer, it's plus there.
It's plus here, yes.
Should it be multiplication or should it still?
No, that's correct.
Oh,
No, that's correct because I use this Young's inequality. In Young's inequality, we have a product here and addition here. And that was a little bit confusing for me. After that, I wrote this, so I made a mistake. So that's a product here for sure, because this is guaranteed. If the real Hölder's inequality is this, we can say that this is our inequality now. But this is the inequality that we need to rely. Okay, but the hard part is what is our goal, and that is the Minkowski inequality, which paves the way that I can prove this inequality in a matter of seconds. So, but this, I hope that I can provide it in a good way, because that is a little bit more technical. So I need a little bit big space. So let me clean what I don't need. So now we want to prove the last inequality. After that, I can immediately, hopefully, prove what we wanted to prove in the beginning. So Minkowski inequality, I will write the same thing. So here I would say that let x1, let me go back to lowercase letters again. x1 and x2, y1 and y2 are real numbers, and p only is a number greater than 1. There is no q involved in this problem. And then we want to prove that absolute value of x1, absolute value of x1 plus y1 to the power of p plus absolute value of x2 plus y2 to the power of p, and then to the power of 1 over p is less than or equal to absolute value of x1 to power p plus absolute value of x2 to power p to the power of 1 over p. And then this time, I'm sure this was a little bit confused. So this is addition again. To the power of p again, y2 to the power of p, and then to the power of 1 over p. It's a little bit complicated formula, but this is the Minkowski inequality if x1 and x2, y1 and y2 are real, and only p is greater than 1. So you see that there is no q involved in that problem. Okay, again, you can say that, okay, if x1 and x2 are simultaneously 0, nothing to be proven, yes? I mean, it's done. Because if x1 and x2 are 0, the left-hand side, so x1 and x2 are 0, this is 0, and this one becomes exactly equal to this one, so equality holds, so it means that this also holds. And if the same thing, if y1 and y2 are simultaneously 0, this is guaranteed. So we assume that x1 and x2 are not simultaneously 0, and y1 and y2 are not simultaneously 0. So, but this is a little bit more involved. I have to concentrate. Hopefully I can represent it. So we start with this combination here inside, not with that power. So I would say that absolute value of x1. But before doing that, let me bring the q in, because you know that in Hölder's inequality, I also have a q, which is guaranteed to be 1. How can I define my q? That's simple, because if p is greater than 1, then what happens? It means 1 over p is less than 1, and of course positive, yes? Okay, and then it means that 1 minus 1 over p is positive and less than 1. This is guaranteed. Do you agree? If 1 over p is a number between 0 and 1, 1 minus 1 over p is definitely positive, because when p is greater than, yes, 1 over p is less than 1, so 1 minus 1 over p is positive. And I hope that you agree this is less than 1 because 1 over p is positive. 1 minus a positive number is definitely less than 1. So what does it mean? This means that there exists a q which is greater than 1 such that 1 over q is equal to 1 minus 1 over p. Is that understandable? Yes? Because 1 minus 1 over p is a number squeezed between 0 and 1. Okay? I define q to be 1 over this number. Yes? And definitely this number is greater than 1. This means that. So this is really true. Yes? So this is the q that I introduce into my problem. Okay? So p is greater than 1. I hope that I could convince you that this is guaranteed that there exists a q greater than 1 so that this holds. In other words, I can say that there is a q greater than 1 such that 1 over p plus 1 over q is equal to 1. Okay, so we will need that one because my goal is to use somehow the Hölder's inequality to prove the Minkowski inequality. Okay, so now I start, so if you don't mind, let me go to this table, to this board, so that I start from the one expression inside, only this expression. Okay, so what I do, I would say that this absolute value of x1 plus y1 to the power of p plus absolute value of x2 plus y2 to the power of p can be written in this form. Absolute value of x1 plus y1 times absolute value of x1 plus y1 to the power of p minus 1. It was actually a very creative way of Minkowski was able to come up with this idea, okay? This is one of those cases that you usually don't think about it, yes? So because it's not clear what we're supposed to do. But then here I can write the same thing. Okay, so let us explain. So what I did, I split this into two parts as the product. I hope that you agree that this is exactly the same thing. And this is exactly the same thing, so that's correct. So what was the motive behind that? Because Minkowski wanted to use the triangle inequality for this absolute value. So we had this before, so if you remember, we proved that absolute value of x plus y is always less than or equal to the absolute value of x, absolute value of y. So we want to use that here. So what happens, this becomes less than or equal to absolute value of x1 plus absolute value of y1 multiplied by x1 plus y1 to the power of p minus 1. And then I have the same thing here, absolute value of x2 plus y2 multiplied by x squared, x sub 2, y sub 2 to the power of p minus 1. And I don't have any problems with p minus 1 because I've assumed that p is greater than 1, so p minus 1 is still positive. So is that understandable? So this is equal to that, but because this factor is less than this factor, the whole combination is less than this, and the same reason for that one. So what I have done is actually quite correct. So now what I do, I expand this expression. So what I do, I would write x1, absolute value of x1 plus y1 to the power of p minus 1. And then I have to multiply this, so let me write it a little bit further. So this becomes absolute value of y1 times x1 plus y1 to the power of p minus 1. So what I have done, I have multiplied this here, wrote it here. I multiplied this here, and wrote it a little bit far away. So what I do next, I will do the same thing here. So I multiplied this here and wrote it next to this. Yes, and then I multiply this and wrote it here, and write it here. Yes? So are you following what's happening? So I decompose it into this part. I use triangle inequality for these things, so I have less than or equal, but then equality comes in, I multiply it, and then rearrange them. Okay, but what I want to do, I want to use the Hölder inequality for this part and that part in a very creative way. So what do you think I will do here? I want to use the Hölder's inequality as you see on the board. So, what can I do? So let us concentrate on this piece for the time being. You see, I want to have this combination. Yes? So you see, this one and that one, okay, is going to play the role of the first term somehow, and this one is going to play the role of the second one. Okay? So what can I do?
You can just say that x1 is just x1 again, and y1 is equal to
the whole expression. Exactly. So I will do the same thing. So this little absolute value of x1, so little x1 is the same as capital. So if I give the role of capital X1 to little x1, and I give the role of capital Y1 to x1 plus y1 to the power of p minus 1, then I can use this, and I will do the same thing here. So hopefully you agree with me, this part is less than or equal, okay, capital X1 absolute value to power p, so this becomes absolute value of x1 to the power of p plus absolute value of x2 to the power of p, and then to the power of 1 over p, okay, multiplied by, okay, can you tell me multiplied by what to make sure that you really understand what's going on? So I want to use Hölder's inequality that you see here and write something for these two terms, okay? You see that this one and that one to power p are these numbers, and this one and that one to power q are the second numbers. Okay, and what is the sign between them is multiplication. So I put the multiplication here, this one and that one to power p to power 1 over p. What do I write here? What do you think I will write here?
will it be too nested actually?
Yeah, it is a little bit messed up, and that is the genius of actually Minkowski. He didn't care. He knew what's going to happen by doing calculations. So what we do now here, this one, can you tell me what should I write? I just want you to tell me what should I write here. Okay, can you tell me what is the power here?
Oh yeah, I should write it.
What's the power?
1 over q.
1 over q, yes. And then what do you have here? You have this number, whatever it is, to the power of q. So this means that I have this number to the power of q. But then q will be multiplied here.
Oh yeah, right.
Yes? And the same story for the next one. Yes? And then I use Hölder's inequality once more for the second combination. So then what will happen? The same story, yes? So this becomes absolute value of y1 to power p plus absolute value of y2 to power p to the power of 1 over p, but multiplied by the second ones to power q. So this becomes x1 plus y1 to the power of the same reason. So let me just not explain it. The power is 1 over q. Do you agree with me? So to be honest, it is a complicated way of thinking, you know. So Now it's promising. Why? Because I have these two combinations that I need. You see, in Minkowski inequality, I want to have this. It's good. I have it here. And then I want to have this with addition sign. With addition sign, I have it here. Unfortunately, this seems a little bit disturbing. But do you have any idea how to get rid of it now? So even the 90% of the job is done, but it's still you have to be creative to understand how to proceed, yes?
Can we like rewrite Q as in terms of P?
Yeah, exactly. So we need to do something with this combination which is appearing 4 times in our problem. If I can do something with that, but do you have any idea what to do with that? I want to have the combination of Q times P minus 1, so this motivates me go backward. For example, here, so let me take the common denominator there, so 1 over Q is equal to P minus 1 over P. And then this times that is exactly finally the combination that I need is equal to this times that. So this weird thing is just P. Yes? So I can just replace that with P. But be careful, the problem is not still finished. So again, equality. So don't get confused. I started with equality, inequality, equality, inequality, and then again equality. So what can I write? It can be absolute value of x1 to power p plus absolute value of x2 to power p, then to the power of 1 over p. But I can write the second term simpler by just writing x1 plus y1 to the power of p instead of that weird combination of q times p minus 1 plus absolute value of x2 plus y2 to the power of p, but to the power of 1 over q. And then the next one is absolute value of y1 to the power of p plus y2 to the power of p to the power of 1 over p. And then I will have exactly the same combination. So x1 plus y1 to the power of p plus x2 plus y2 to the power of p, and then to the power of 1 over q. Are you with me? Yes? Okay, then what? But this is promising, look at it. Yes, I am very close to what I want to prove. Look at the formula that you want to prove. Where was it? Here. Okay? This combination and that combination are really there for me. There is one thing disturbing me, and there is a good point about that disturbing part, is that it is common to both of them. You see, this one is exactly what you see here again. Yes? So I can again go equality sign and factor that disturbing part out. Yes? And what is left from this one? And plus yes. I think it's very promising now, because exactly what I need in Minkowski's inequality appears there. But of course, it's not done yet because I have a little bit of disturbance here. And so what do you think I do? So don't get distracted. This is my starting point. I was able to show but a sequence of equalities and inequalities. I was able to show that this expression, whatever it is less than or equal to this expression at the end. Yes? But there is more or less 1 or 2 steps left. Look at the original inequality you have. In the original inequality, you don't have this exact combination. You have this combination to the power of 1 over p. What I have shown so far, I have shown that this is less than or equal to this expression. So this motivates me to do what? Yes, but how? So if you want, I can write it here for you so that it becomes in front of your eyes. So instead of having this, so let us not distract you. I will take this one and paste it here. Might be you can see it better. Absolute value of x1 plus y1 to the power of p plus absolute value of x2 plus y2 to the power of p is less than or equal to this combination. So far we have this. So what is the next step we want to do?
Yes, divide.
Yeah, just divide by that expression because I want to have only this. So this is a very simple step to take. I divide that by that expression. So what happens? So then let me just write it once. So it becomes this one to the power of p, x2, y2 to the power of p divided by x1 plus y1 to the power of p plus x2 plus y2 to the power of p and then to the power of 1 over q is less than or equal to absolute value of x1 to power p, x2 to power p, and then to the power of 1 over p plus y1 to the power of p, y2 to the power of p to the power of 1 over p. But this expression and that expression are the same, so in principle I can write it to the power of 1. And then I have two numbers, two exponents divided, so this becomes 1 minus 1 over q. But 1 over 1 over q is just 1 over p. Yes, so this becomes absolute value of x1 plus y1 to the power of p, absolute value of x2 plus 2 to the power of p, and then to the power of 1 minus 1 over q is less than or equal this expression. But if I ask you what is this is nothing except 1 over p. So this means that finally we were able to show that this inequality works. So you see that this is one of those problems. This is exactly at the right level of high school mathematics, but extremely complicated. So you have to have a very brilliant mind to be able to come up with this kind of proof. Okay, but now the last step. How can I use Minkowski inequality finally to prove my question mark? Yes, so let me just, and that is enough space to write it down. So my goal was to prove this inequality. It's a matter of just renaming or relabeling. So how do you think I will use Minkowski inequality, which is written here, to prove this inequality?
Like, we'll do that thing again where we say that like alpha is, let's see, would it be 1 minus 2 at the
Yeah, exactly. So what I will do, I will introduce in the Minkowski inequality that you see here, I would say let x1 to be what? To be a1 minus a3, and y1 to be a b1 minus b3, yes? No, sorry. A3, so I want to have a1 minus a3, so let me write it like this. If I introduce x1 like this and a y1 like this, and I introduce, then what will happen? Then when I add them, this becomes a1 minus a3, which is exactly the combination that I need. Yes? Okay, so this is what we do. So x1 is this, y1 is that, and then x2 is what? b1 minus b2, and y2 is b2 minus b3. So now because this Minkowski inequality is valid for all choices of x1, x2, y1, y2 in R, so I will pick up these numbers that is given in this inequality and construct my variables and put them back into the Minkowski's inequality. I hope that you agree that we are done. Yes? Because x1 plus y1 becomes exactly a1 minus a3, and x2 plus y2 becomes exactly b1 minus b3. Okay? And then I put them here. So this 1 to the power of 1 over p becomes exactly the combination that you see here. And then this one, x1 is this, x2 is this, becomes exactly that combination. And y1 plus y2 by these choices becomes exactly that combination. So finally, we were able to show that this is valid. So we actually started with an abstract, with the notion of distance. We abstract the properties of the distance out, and then we define the metric, and then explored some metrics. The natural one was the Euclidean metric, and then we also learned about the taxicab metric. And then from there, we were motivated to see that how can we generalize the problem. We were able to generalize the problem, and then there was one main obstacle in front of us, and that was proving the triangle inequality for the functions that we had in mind. And then finally, by these three inequalities, we were able to show that that is the case. So it means that we have a big class of metrics, okay, so that we can have. Okay, so one good question is, what do you think will happen? Because first of all, by the way, there is nothing here to prevent us to have fractions. So don't think that p's are natural, even though we started with natural numbers, but everything was proven. So for example, p could be simply 3 over 2. So we can have a metric of like this, yes, instead of p. And the point is that I have a sequence of metrics. Say D1 is the taxicab metric, D2 is the Euclidean metric. For D3, D4, etc., we don't have names. Let us stick to the case that p is a natural number. Then I have a sequence of metrics that is proven here. Okay? And then the question is that, what do you think will happen now? Even the imagination goes, the imagination of mathematicians is like this. Now they say that, okay, what will happen if this number goes to infinity? Do I have a metric or not? Okay? Okay, so the question is that, what will happen if I have this metric and then I send p to infinity? Okay? Of course, I should have really defined what does it mean to send a sequence of functions when the sequence number goes to infinity. Okay, but everything that you see is exactly coming in this way. So this is something that mathematicians think about it. How can I talk about the sequence of functions and things like that? And then there is a metric. It is very interesting that this really approaches to another function, which is indeed a metric again. It's very interesting. So the metric is, for this reason, called d infinity. And then the point is that, what is your guess for this? If this d infinity is the limit of this function metric, yes? It is very interesting. It turns out to be, it's the maximum of the absolute value of x1 minus x2 and absolute value of y1 minus y2. And the question is that, is this also a metric again, even though that's the limit of some metrics, but is it the case at the end that this becomes a metric? Okay? And it's a good idea, if you have time, we'll look at it in GeoGebra to see how it goes. So let me remind you, do you remember, if I want to use the Euclidean metric, and let us say that I want to find this circle around the origin and radius 1. So it is really a circle. You remember in Euclidean metric. But in taxicab metric, I don't know if you remember or not. What was the circle? The same circle, the same center and the same radius, but using the taxicab metric. It was a square, if you remember. So it was a square like this. So this one is a circle with radius 1, if I am using the Euclidean metric. But if I use the taxicab metric, I hope that you remember we were able to draw it. It was this square. And this is a natural question. What do you think this circle will look like? Yes? And then we continue this one. So let us explore a little bit what is happening by GeoGebra, okay? So if I go to GeoGebra, so let me just draw ABS of x. Yes, so this is ABS of x plus ABS of y equals to 1. And that is the circle, that is the square. Let me make it a little bit bigger. Okay, now let me go and write ABS of course ABS is not necessary here, but let us stick to that. ABS of x, ABS of x, and then to the power of 2 plus ABS of x, ABS of y, to the power of 2 is to the power of 2 is equal to 1. And that is what you expect. That's the circle. Okay, now let me increase this ABS of x to the power of 3 plus ABS of x, ABS of y, to the power of 3. Yeah, so I am increasing this one. So I will get something like this. I don't know what the name is, but it is getting a little bit smoother. I mean, yeah, it's something like this. You see it on the picture. And let me just do it once more. I just do, because there is no difference between absolute value on x if it is even power. So let me just skip absolute value signs, and then you see what's happening. Well, so what is your guess? What do you think will happen if I start increasing this number higher and higher? So if you want, you can see it a little bit better here. So you have an idea what's going on. If you want, I can raise it to a 5th power. You see what's happening. So ABS of x to the power of 5, and then I have plus ABS of y to the power of 5, okay, and then is equal to 1. So it's clear what's happening, yes? And let me, I don't know if GeoGebra is capable of doing it. Let me raise it very high, so let me write it even, x to the power of 50 plus y to the power of 50, and then this is equal to 1. So what's happening, do you think? The last one is for only 50. So what's happening for this metric? What do you think? If I raise the power, I started from square, then when p is 1. For p2, it becomes a complete circle. And when I start increasing the power, I am getting closer, and to what shape do you think? Again, a square, but a little bit tilted square. And that's exactly what's happening. So that's a good exercise for you to try to draw the graph of this one, the circle. So use d infinity. So I want you to explore that if you do that, what you guessed is really correct. I want you to draw the circle, but using this metric, and you will really see that this is a complete square in that orientation. So this means that this is also very nice. We were able to discover a new metric. And what I want you to see, try to convince yourself why suddenly, when I increase this number, d infinity becomes maximum. Yes, because it doesn't seem like that, yes? In all these metrics, I have addition, yes, between these type of expressions with some powers. But suddenly, when I go to infinity, it becomes this number. Of course, it needs a little bit, it needs a theorem if you really want to convince yourself. And the theorem is this. If you have a sequence an, squeezed between two other sequences. This is a theorem that you take it for granted if you want to think about this problem. And the theorem is this. If you have a sequence which is squeezed between two sequences, and coincidentally, the limits of the left and the limits of the right are the same, then the limits of the one squeezed between them will be the same. Okay, so that is called a squeezing theorem. It is reasonable, it's not that hard to, it's not very strange intuitively, but of course, you need to prove it rigorously. If you want to think about this problem, why d infinity takes this form, you have to know this theorem in order to be able to show that. So taking it for granted, you should be in principle able to convince yourself that this is indeed the case. Of course, I will make some videos and exercises, and then I will discuss about that myself. Okay, so I think this is the last part I wanted to talk about abstraction. Hopefully you realize the idea of the abstraction is helpful. And it actually generates a lot of ideas and mathematics out of just abstraction, yes? So might be people didn't even think about these kinds of inequalities. It was not discovered to us if we were not curious enough to talk about, to explore these things abstractly. Okay, I will make some exercises as usual, and I try. Of course, I am very busy these days, but I will try to make exercises for each session and solve them one by one. So you will not learn unless you really do the exercises yourself. Okay, so the goal of this lesson was to show that some questions are really technical. So we didn't add anything conceptual to our framework today, but this is also something that you need to expect in pure mathematics and applied mathematics, of course. Any questions? Okay, I don't know where the next lesson will be, but we will start a very formal lesson on mathematical logic. Yes. Okay, thank you very much.